Alright, so this is from my notes for a computing course, so in Python, which I'm taking. And right, so the topic of discussion for this video is 0.1 plus 0.2 equal to 0.3. Is this equality actually going to give us false? It should be true, right? I mean, from a mathematical point of view, it should be true. But then if I actually run this code, it gives false. So why does this happen? So first what I'm going to do is I'm going to tell you what 0.1 plus 0.2 is actually stored as in the computer. So if I run this, it gives 0.3, but there's something attached to it like 0.00004, stuff like that. Why does this happen? So this prints false because the binary representation of these numbers are recurring. So you can't actually write 0.1 in binary without like a recurring representation. So these are stored as approximations because of course you don't have those many decimal places, right? In real life you can't do that. So what the computer does is that it approximates till some decimal places, and then it adds, and then it approximates again, right, to some decimal place, and this is what we get finally. And then when we check the equality, it says it's false because this is of course not equal to 0.3. So thus when we say 0.1, the computer actually stores it as like 0.99999999946, some other shit. Okay. So first of all, you might have a question, well, why can't we store 0.1 in binary, right? So usually for any integer, you can actually write it in a binary format with finite number of digits, right? But what happens with floating point numbers like this? So let's go to something simpler. 0.2 is 1 upon 5. So assume that we can actually write that in binary. So it will be like 0.101 whatever, right? Something, so some string of ones and zeros over here, right? And this is in binary, of course. So this can be also thought of as the same string without the floating point, right? And that upon 2 to the power of whatever the length of this string is, right? So let me give an example. Let's just say 0.101 in binary. This can be thought of as 101 in binary. Of course, this is going to be in binary. And that upon 2 to the power of the length of this, which is 3, so 2 power 3, right? So this is not just for binary, but for any kind of number system you can do this. So like, you know, 0 point something, some string of digits in that base, that in that number system, right? That can be thought of as this thing in that number system as an integer, of course, right? Without the decimal point, without the floating point, because now it's not decimal number system. And that upon the base to the power of length of this, the length of this string, right? Yeah, so you know, for 10 it's pretty easy, just 101 base 10 upon 10 power 3, right? And that's going to be equal to 0.101. Similarly, you can do it for binary. So like the way we are doing this is that if you have something like the 0.xyz, right, you can think of it like x times b power -1 plus y times b power -2 and so on, right? So what we can do is multiply divide by the the powers of base to make the denominators the same. So the base to the power of length of this string. So then, you know, this is actually just a 3-digit number, right? 3 character string, that's what I should say. It's like z times b power -3. So what we can do is, you know, we'll just have this b power -3 taken outside. So like we are making that common. We got b power -3, right? So the largest number over here, we'll just take that we'll just take that out, which is of course going to be the length of this thing, right? Because you've got 3 of these. This is b power -3. That makes sense, right? That's just the way this works. So b power -3 out, then this is like x times b power 2 plus y times b plus z, right? So z times b power 0. So you will start off at 0 over here, then 1, and then 2. So this is the same thing as b power -3 times xyz in the number system with base b. So that's what I was saying. We can write it as xyz base b, and that upon the base b to the power of the length of this thing, which is 3 in this case, right? So the same stuff is going to be done for 2 over here, right? So suppose you can write it like this using finite number of digits, then what you're basically saying is that you can write it like this. So this thing, even it's in base 2, this is basically some kind of integer, right? Yeah, because all the operations over here will be integer, right? 2 to some power, that's integer, that times some other integer, the digits which are 0 and 1, integers, addition between integers, that also gives integers. So this thing basically is an integer. So what we are saying is we are writing it as some integer upon 2 to the power of the length of this string, and if this is like not 0.0 or something like that, so like there is some length, then this thing is also just some integer which is positive, right? So it's a natural number, let's just call that n. But what that means is that 2 power n is equal to 5z, right? And of course z is not 0. But what that means is that 5 divides 2 power n, which doesn't make sense because this does not contain any 5 factor, right? Which means you cannot write it like this. So using finite number of digits, you can't actually represent it in binary. So the way we are going to do that is, so like let's figure out some way to represent some certain number. Say for example 0.5. How would you represent this in binary? So assume that we already know how to represent it in binary, right? So it's like 0.xyz stuff in binary, okay? Just keeps on going. So what we can do to figure out what x should be and what y should be and so on is that we can like multiply this thing by 2. So this times 2, what this gives is x point yz so on in binary. So now this is the fractional part, we know it's less than 1 and all that stuff, and this integer part is the first digit over here, right? That makes sense. So multiply by 2, take the integer part, put that as the digit, right? The next digit in whatever sequence you're writing, and then once we are done with that, forget about this completely. It's not like 0.yz, and then do this again, do this once again. So times 2, you get y point z and whatever other shit is over here, and this is in binary, right? And then once again, so like here when we did this, we output x as the digit, here we output y as the digit, then forget about this, then once again like we'll output z as a digit and so on, right? So in this way you will basically form this series, 0.x, right? This x is going to be here, then you got y over here, and then you got z over here, right? So let's try it out with 0.5 first. So 0.5 times 2, right? That gives us 1.0. So we'll just cancel this stuff, we'll output that. So the first digit would be 0.1, right, in binary. So yeah, we just cancel that, and then you just get 0.0, and that's it. That's where we'll stop, right? So once you get 0, stop. Let's try for something more complicated. Let's try for 0.125. So we know it's just 1 upon 8 and it's like 2 power negative 3, but still let's try to do this. So this times 2, yeah, that just gives us 0.25. Take this and put that as the first digit, so like 0.0, okay. Well, this times 2 once again, so this was the output for the first step. Then the next one, we'll just have 0.5 once again, this is 0, so just 0.00, right? Just that output, fine. Then next you multiply by 2 once again, 1.0. So now the output is 1, so now our number will be like 0.001, and then you make this 0, right? You cancel this 1 and then you make this 0, and there you go, you got 0.0. That's where we should stop. So this thing base 10 is actually written as this base 2. Makes sense, right? This thing is 2 power negative 3, so 1 times 2 power negative 3, this is obviously 1 upon 8, 2 power negative 3. Let's try it out for 0.2, which is 1 upon 5, and let's see what happens. So yeah, as always, multiply by 2. Let's see what we get. We just get 0.40, right? So 0.0. Then we multiply by 2 once again, you get 0.8. Once again it's just 0, so we put another 0. Then by 2 once again you get 1.6. We put 1 here because that's there, make that 0. Then 1.2, right? So put 1 there, make that 0. Then 0.4 and so on. So now it just repeats, right? So like 0.001, next is going to be 0011 once again. This is recurring, and this is in base 2, of course, right? So that's what I was saying, that you will get, you know, not finite digits. And of course you can verify this GP, which is basically like, so this is like 3 upon 2 power 1, 2, 3, 4, so 3 upon 16, right? And this is 2 power negative and 2 power negative. So yeah, this is definitely 2 power negative 4, I guess, right? So like it's 3 upon 16 first, then you got like 0011, so that's like plus 3 upon 16 square, and so on, right? This is what this GP is. Now this is going to be 3 upon 16, 8 times 1 upon 1 minus r. So 1 minus, so 1 upon 1 minus r is just 1 upon 16 over here, right? That's what this infinite GP will be, which is, you guessed it, so like this is 15 over there, that goes up on the top, 16 that cancels, so it's 3 upon 15, which is just 1 upon 5. So yes, it's verified, this thing is 1 upon 5 and everything, but you don't have a nice representation of this thing. So instead it's the sequence, an infinite sequence, right? So how will our computer store this? It cannot store it. So what it does is that it rounds it, or like stores only some digits or something like that. And that's why this is happening. That's why 0.1 plus 0.2 is not exactly 0.3, it's some other thing, right? Because the computer takes approximations. It doesn't like store this infinitely long sequence. It can't, right? Yeah, that's what I wanted to say. Okay, then I'll see you guys in the next video.